Now, let me show you something about a normal distribution. And this is a Galton board, that's what this thing is called. And Galton was this incredibly intelligent polymath from the late Victorian times who made contributions in a whole variety of scientific disciplines, psychometrics being one of them, the measurement of human behavior. Galton is often regarded as the first person who studied intelligence, but that's not true actually. Galton studied what he called eminence, and eminence was sort of the probability that you'd be in the same class structure, say, as an aristocratic Englishman, and he thought of that as an inborn trait, you know, which made the British aristocrat superior to the British commoner, and then, of course, superior to everyone else as well. And people confuse that with intelligence, but if you read Galton carefully, you find out that he didn't conceive of intelligence. It was more like talent or ability, well, or eminence, which is what he called it. So now Galton was interested in measuring things, and so he made a lot of measurements of people, various aspects of people, physical aspects, and he started to develop some of the presuppositions that we use in our statistics today. And one of the things he noticed was that a lot of things that you can measure, like height, are normally distributed, which is to say that most people are average, and there's a distribution around the sides, so that most people are average, a few people are really tall, and a few people are really short, and it's kind of a continuous distribution across that entire span. And so that's a normal distribution. Now, the theory is that things are normally distributed when a lot of different factors contribute to them. So you can imagine in the case of height, well, what might contribute to it? Prenatal conditions might be one. Nutrition might be another. Genetic heritage might be another, which you could also divide into the genetic component you get from your mother and the genetic component that you get from your father. Posture, gender, those are a few. Maybe ethnicity. The Dutch, for example, are extremely tall. So there's a variety of factors that might contribute to height. And when a variety of factors contribute to something, then it tends to be normally distributed. That's the hypothesis. And that's because the variation is random. So let me show you what it means for variation to be random. Now, so Galton figured this out. Now, this is a Galton board. Now, what a Galton board would normally be would be a board with nails. So each of those little dots there, you can imagine those are nails. And then it would be slanted a little bit, and then there'd be a spout at the top, right in the middle, that would drop marbles down. And then at the bottom, there's a bunch of containers where the marbles could land, and then you can see how the marbles distribute themselves if you let them fall randomly. Now, this is random because at each nail, imagine a nail is a choice point, right? The marble can go right or left, and it's entirely random. And so here's what happens if you run something randomly. Now you can see as the balls accumulate, or the marbles accumulate, that there's starting to be considerably more in the center and considerably fewer out on the edges. Now the technical reason for this is that there's lots of ways to get to the middle and hardly any ways to get to the edges, right? Because if you want to go all the way to the right, for example, then you'd have to, there we go. If you wanted to go all the way to the right or the left, then every time you hit a nail, you'd have to go either right, so right, etc., or left, etc. And you can imagine, since there's only a 0.5 probability of each of those, that once you have 10 or so of those stacked together, the probability that you're going to take that particular path is vanishingly small. Where in the middle, there's all sorts of different ways you can get there. Right, left, or right, left, or, well, you get the picture. There's all sorts of ways. So there's more paths to the center than there are paths to the edges. And so that's why you get a normal distribution. And the normal distribution does some pretty weird things. So for example, we'll go to this next one. This is another kind of Galton board. And we'll run the first part of it, and you'll see that you get your typical normal distribution. So you could imagine that each of those little nails is a factor in some sense, a random factor determining where you end up in the distribution. Okay, so after we fill this up and we have a normal distribution, then you see the little yellow and black line there. We're going to take that out, and then the balls are going to fall again. What do you think will happen when they go to the next level? Any guesses? Yeah.
More likely to go to the edges.
Okay, so that's one hypothesis. The balls will be more likely to go to the edges. Anyone else? What do you guys think?
It'll be a more flattened distribution.
Be more flattened? More flattened? People agree with that? Okay, so we better withdraw it quickly. It's starting to stack up here. So, okay, let's see what happens. Lo and behold, if we kept running this, you'd get another normal distribution. So it actually doesn't change it a bit. So the normal distribution is a pretty robust phenomena. So now, if you're doing basic statistics, let's go back to that for a minute. What you're really trying to do is to figure out what the probability is that two distributions will overlap. So for example, let's say you took the distribution of height among women, which is about 5'4" on average, and so there'd be a normal curve around that, because there's some very short women and some very tall women, and then there'd be a normal distribution around men, and men are on average 5'9", and then you could calculate the probability that those two curves were the same by chance, and that would depend to some degree on the number of people in your sample. So to do the statistics, you need the two normal distributions, you need the number of people in the sample, and then you need a way of calculating the probability that those two distributions could have been drawn from the same population. So that's your hypothesis, basically. That's the null hypothesis, is that the two samples are drawn from the same population, in which case there's not going to be any difference between them. Or there's going to be random differences between them. And the cutoff point is that if the two samples you draw have normal distributions that overlap in such a limited manner that would only happen in 1 of 20 cases, right? So you're drawing random samples from the population, then you presume that that's a significant difference. Now it's arbitrary. That's p is less than 0.05. It's arbitrary. Now you might say, well, why did psychologists pick p is less than 0.05? And the answer to that is, there is no reason except that there's two errors that you can make when you're calculating your statistics. One error is you find a difference when there isn't one, right? You find a difference when there isn't one. And the other is that you don't find a difference when there is one. And those are type 1 and type 2 errors. And what you're trying to do is to minimize both of them simultaneously. And you can't say where that's most suitable, because by reducing one error you increase the other. So psychologists had to pick some cutoff, and 0.05 seemed to be as good as anything else. So now here you want to look at this, because actually you really need to get familiar with what a normal distribution looks like and the ways that it's parsed up. So you see right at the center, that's the mean and the median and the mode. If the distribution is perfect and normal, those three things are going to be the same thing. At the next level there, you see percentage of cases. So at 3 standard deviations below the mean, there's only 0.13% of the population that's 3 standard deviations below the mean, or 3 standard deviations above the mean. So we could say, we can think about IQ, because people are sort of cognizant of IQ to some degree. 100, which would be the mean in terms of IQ, is the average IQ of someone who's your typical high school graduate. And then 115 is the IQ of your typical state school graduate in the US. So there's a difference of 15 points, and that corresponds, if you look here in terms of percentages, which is the bottom line, is 50% of people have an IQ above 100 and 50% have an IQ below, and it's because it's defined that way, by the way. And then if you go up one standard deviation, you see that we'll say 85% for the sake of simplicity, 85% of people have an IQ below 115. And then if you go up 2 standard deviations, you see that 98% of people have an IQ below 2 standard deviations, and 3 standard deviations is 99.9. So when you get up to 130, there's only 2.5% of the population has an IQ that high. That's about where you guys are, somewhere between 120 and 130. So, you look around and you think, well, this is an average class of university students, but you're not average in terms of intelligence, and that makes a huge difference, because intelligence is one of the best predictors of career success, for example. If you go out to 3 standard deviations, that's an IQ of 145. And there's undoubtedly a couple of you in here. It's 1 in 1,000 in the population. There's a couple of you in here that have an IQ of 145, or maybe more than a couple. Now, one of the things you want to notice is, because people get very confused about this with regards to percentages, so let's say that you were assessing 2 people to hire them, or you were assessing them for their intelligence, which is something that might be done, for example, if you were screening them to go to university, because the SATs do that in the US, or if you were screening them using the graduate record exam. And you have one candidate who's 98th percentile, and the other candidate who's 99th percentile. Okay, so think about that for a minute, 98th, 99th. Where is there more difference? You have 3 candidates. One's 85th percentile, one's 98th percentile, and one's 99th percentile. Where's the biggest difference? Is it between the 85th and the 98th? Yeah, in terms of improbability. So it's the same distance. Now that's what you have to remember when you're thinking about percentiles, because 99 and 99.9 percentile don't sound very different, but they're the difference between 1 in 100 and 1 in 1,000. So it's a huge deal. That's why you see that the normal distribution is divided up into these standard deviations, and those are basically identical differences. And those are often identical differences in terms of ability. So for example, you might think that once you hit 130, going above that isn't going to matter, but that's not right. There's just as much difference between someone who has an IQ of 130 and someone who has an IQ of 145 as there is between someone who has an IQ of 115 and an IQ of 130, even though the percentiles start to switch around. So you need to know these sorts of things when you're starting to think statistically, because otherwise, well, you can't understand what you're doing, and that's generally not a good thing. So, although it's very frequent.